Okay, now we look at a series bandpass filter example, and this filter is a little bit different than the one we were looking at in the previous videos because this one has a non-ideal inductor that's shown in the red box. So in addition to the inductance of 100 millihenries, we're also considering the resistance of the wire, which is 10 ohms. And then here's our R at the output, and here's a capacitor of half a microfarad. So we're just going to go ahead and calculate some various quantities that you're typically interested in a circuit like this. First of all, the frequency response equation, okay, V out over V in the magnitude, would look something like this, where we have 100, the resistance across the output in the numerator, and then we got square root of 110, okay, because this is the 100 plus the 10 ohms of the resistance of the inductor. So 110 squared plus omega L, which would be 0.1 omega minus 1 over omega times half times 10 to the minus 6 since it's micro. Alright, and then all squared. And you know, we could find V out in terms of VI, and you can see here VI has an amplitude, a peak value of 10. So we could find, you know, the peak value of V out for various omegas just by plugging into this expression, this frequency response equation. But I'm going to show you a different way in just a moment, where we can use what I call a circuits approach to find what V out is at various omegas instead of just plugging into this equation. And I like the circuits approach just because I think it gives you a better understanding of what's actually happening as opposed to just solving a mathematical equation. So before we find V out or a particular omega using that circuits approach, one thing you're often interested in a circuit like this is what the resonant frequency is. So remember, at the resonant frequency, that's when we have this equality between XL and XC. The reactances of the storage elements are the same. So as we showed earlier, the resonant frequency equation we just solved for omega in this equality is just 1 over the square root of L times C. So if you put in 0.1, and actually this 0.1 henries, because that's 100 millihenries, and then times half a microfarad, so half times 10 to the minus 6. Okay, so 1 over root LC with those values comes out to a resonant frequency of 4,472 radians per second. And as I mentioned also in a previous video, omega radians per second is equal to 2 pi f, where f is in hertz or cycles per second. So if you wanted this resonant frequency in hertz, you just divide by 2 pi. Okay, so the next thing I'm going to show you is how we can solve for V out at the resonant frequency by using a circuits approach. So this is going to be when omega equals the resonant frequency circuit. So we're going to take our original circuit and put in the ohm values at this frequency. So first, our source and phasor form is just 10 and an angle 0 volts. And then the impedance of a 10 ohm resistor, which is the part of the resistance of the non-ideal inductor, is just 10. And then also we have the resistance out here at the output, okay, which is 100 ohms. Right, and that's where we're getting our V out across. The V out is across that 100 ohm resistor. Well, now what I'm going to do is replace the capacitor and the inductor with the equivalent number of ohms that the storage elements have at this resonant frequency. So as we just stated a moment ago, the ohms of the inductor equals the ohms of the capacitor at the resonance, right? Because the reactances are the same. And since XL is on the plus J axis, right? XL is on the plus J, and XC is on the minus J axis. Well, if they're equal, since they're 180 apart on the J axis, together in series we would add those, and when we add them they cancel out and have 0 ohms. So you see at the resonant frequency the capacitor and the inductor together act like a big old short. So we can find V out just by doing voltage divider equation, where we would have 10 times 100 over 110. Alright, so V out here at the resonant frequency would just equal 9 it would just be equal to 9.09 volts. Okay, and that's the same as what we would get with the frequency response equation here, that if we plug in, or if we cancel out XL and XC, right, we'd get 110 over the square root of 110 squared. So that would be 110 divided, or excuse me, 100 divided by 110 squared square rooted, which is 100 divided by 110. So you see V out over VI, the ratio would be 0.909, and then since V in is equal to 10, we'd get the same answer of 9.09. So just a different way, a different approach to get the same answer of V out using this circuits analysis as opposed to just plugging into the frequency response equation. Okay, well we can also get the V out for let's say omega equal to 0, okay, 0 radians per second, okay, which is DC. So at omega equal to 0, that's when your capacitor has infinite ohms, right, because you'd have 1 over omega c where omega is equal to 0, so 1 over 0 is infinity, and XL is 0 ohms. So again, this is the capacitor. So the capacitor is acting like an open, and the inductor is acting like a short. So your circuit would look like this. You'd have your 100 ohm resistor, then the inductor would be a short, the capacitor would be an open. Okay, so 10 at an angle of 0 volts, 10 ohms, and then 100 ohms. Okay, but you see V out here would just be 0 since the capacitor is acting like an open, no current is flowing, so V out would just be 0 volts because there's 0 current through this 100 ohm resistor. And then for omega equal to infinity radians per second, well, you'd still get V out equal to 0 because now the inductor would be acting like an open, right? Because omega L, infinity times L would just be infinity, and XC would be 0 ohms because you'd have 1 over infinity, which is 0. So at omega equal to infinity, now the inductor would be an open, the capacitor would be a short, but it doesn't matter as far as this voltage at the output's concerned, because wherever the open is, it's going to cause no current to flow through the 100 ohm resistor, and therefore make the output voltage equal to 0. And you would get the same answer from the frequency response equation. Okay, a couple more things and then we'll end this video, and I'll finish the problem in a second video. But a couple other quantities that we can find fairly quickly would be the quality of the inductor, and this quality of this inductor will take at the resonant frequency. Okay, that the inductor was designed for resonant frequency, so the particular omega would be omega naught. So we would take our resonant frequency of 4472 radians per second, and that would multiply times 0.1 Henry, okay, 100 millihenries, which is 0.1 henries, and then divided by the resistance of the inductor, which is just 10 ohms. So this would come out to a quality of the inductor of 44.72. And again, remembering that quality of inductor is an efficiency rating, this basically means that the inductor is storing 45 times more energy than it's dissipating. And then quality of the bandpass filter, okay, quality of the series bandpass filter, that would just be the same omega naught L, but now divided by the total resistance in the circuit, which would be the two resistances added. So 110 ohms. So same numerator divided by 110, that gives you a Q of just over 4, okay, 4.07. Okay, which is less than 10. So your frequency response curve would be asymmetric. Right? You couldn't assume symmetry, because remember, symmetry for all practical purposes occurs when the quality of the bandpass filters at least 10. Okay, so this is a good stopping point. There's a few, well actually at least several more quantities we'd like to calculate for this problem, but I'll do that in the next video.